Everyone, I am Valli Rani from Ramchandra College of Engineering, Eluru, Department of Physics. In this video, we are going to discuss about interference in thin films by reflection. In past, already we discussed about what is meant by thin film and how the colors appearing on the surface of the thin film when it is exposed to sunlight. But in this case, we derive the expressions for bright and dark fringes in thin films. For this, we consider a monochromatic light wave of wavelength lambda is incident on a thin film of uniform thickness. The waves reflected from upper surface interfere with the waves reflected from the lower surface. That is, the two reflected light rays are derived from the same light waves so that they can act as a coherent light waves, and these two reflected light rays are superimposed with each other and produces interference pattern in thin films. Now, we derive the conditions for bright and dark fringes in this interference pattern. For this, we consider a uniform thickness of the film. It has a refractive index mu and thickness of the film T. It has upper surface PQ and the lower surface is P dash Q dash. Now, a monochromatic light wave of wavelength lambda is incident on the upper surface of the film, and this light ray incident on the upper surface at a point A. At this point, the incident light beam gets divided into two parts, a part of light reflected back into the same medium and traveling along the path AR, and the another part of light ray refracted into the thin film and traveling along the path B with angle of refraction R. This refracted light beam incident on the lower surface of the film, and it will get again divided into two parts. Part of light reflected back into the film and traveling along the path BC, and another part of light transmitted into the air medium. And this reflected light ray come outside like this and traveling along the path CR. Here, these two reflected light rays are superimposed with each other and produce interference pattern in the thin films. Now, we derive the conditions to find the conditions for bright and dark fringes in interference pattern. This bright and dark fringes, that is the maximum and minimum intensities will be most depends upon the path difference between these two reflected light rays. Now, first we find out the path difference between these two reflected light rays. So, to find the path difference, we are finding the path difference between these two reflected light rays. We draw a perpendicular line CD to AR. Above this perpendicular line, these two reflected light rays are traveling equal distances, and below this perpendicular line there exists a path difference between these two reflected light rays. Here, the first reflected light ray completely travel in air medium, and the second light ray traveling in a thin film. The second light ray traveling more distance than the first reflected light ray. Now, we find out the path difference between these two light rays. So, that is the path traveled by the light ray in film minus path traveled by path in air. That is, now, to find the path difference between the reflected light rays, for this, draw normal CD and BM to AR and AC. Next, the path difference is equal to path in medium to minus path in air. So, path in medium is AB plus BC. So, path in medium is AB plus BC minus path in air is AD. Next, here the second refracted light beam completely traveled in a thin film with refractive index mu. Now we will consider its refractive index mu. So path difference is equal to AB plus BC into mu minus AD. So AD is the path traveled by the first reflected light beam, which is traveled in completely air medium. For air medium, refractive index of the air mu is equal to 1. Here AD. But here, according to Stokes' law, since the first light ray are reflected at a rarer, denser interface, then there exists a path change to lambda by 2. There exists a path difference lambda by 2. So additional path difference of the first reflected light ray is lambda by 2. Hence the resulting path difference delta is equal to mu into AB plus BC minus the additional path difference added to the first reflected light ray, which is travelled in air medium, AD plus lambda by 2. So this is equation 2. Next, now we are finding the values of AB, BC and AD separately. For this, by using this ray diagram. Next, first we find out the value of AB. First we find out the value of AB. So from the triangle ABM. From the triangle ABM, to find the value of AB, now apply cos R function to this particular triangle ABM. So from this triangle ABM, AB is equal to, cos R function can be applied to this particular triangle ABM. Now cos R is equal to BM by AB, then AB is equal to BM by cos R is equal to BM is equal to thickness of the film. So BM is the thickness of the film. Now substitute this value. BM is equal to thickness of the film by cos R, where T is equal to BM and R is the angle of refraction. Here, triangle ABM nearly triangle BMC. Here, triangle ABM nearly triangle BMC. Because of here, the angle of refraction will be the same. Hence, AB is equal to BC. Here, AB is equal to BC. So, AB is equal to BC is equal to T by cos R. Next, now we can find out the value of AD. Find out the value of AD from the triangle ACD. From the triangle ACD, for this particular triangle, we apply the sin I function. For this, sin I is equal to AD by sin I is equal to AD by AC. Here, AC can be written as AM plus MC. Here, AM is equal to MC. So, AM is equal to MC. That's why we considered as 2AM into sin I. Next, but from the triangle ABM, we apply the tan function for this particular triangle. We get AM is equal to T tan R. Here AM is equal to T tan R, and according to Snell's law, sin I is equal to mu sin R. Now substitute these two values in the above equation 2am sin I. Here AD is equal to AM is equal to T tan R and sin I is equal to mu sin R. So mu sin R is equal to 2 mu T. The tan R can be written as sin R by cos R into sin R. So sin R into sin R, sin square R by cos R. So AD is equal to 2 mu T into sin square R by cos R. Now these values AD and AB, BC values are substitute in equation 1. We get the path difference delta is equal to mu into 2T by cos R. Here AB plus BC. Inside the film, the light ray traveled path AB plus BC. Here AB plus BC is equal to T by cos R plus T by cos R. Here 2T by cos R minus 2 mu T minus AD plus lambda by 2. So AD is the 2 mu T into sin square R by cos R plus lambda by 2. Now simplify this equation. We get thin film, we get path difference between the rays in parallel thin film. Delta is equal to 2 mu T cos R minus lambda by 2. This expression gives the path difference between the two light rays reflected from upper and lower surfaces of the film. Now we find the conditions for bright and dark fringes based on the path difference. So before we're going to discuss about the conditions for bright and dark fringes, for normal instance case, in case of normal instance means if the light ray instant along with the normal, then angle of instance I is equal to 0 and R is equal to 0, and then R is equal to 0, cos R is equal to 1. Then the resultant path difference 2 mu t minus lambda by 2. So for in case of normal instance, the path difference between two reflected light rays is delta is equal to 2 mu t minus lambda by 2. Now we find the expressions for bright and dark fringes based on the path difference. Already we know the conditions for bright and dark fringes is the path difference is integer multiple of wavelength, then we get bright fringe. This is the mandatory condition for constructive interference. So here the path difference is already found, that is 2 mu t cos R plus or minus lambda by 2. Here plus or minus which will depends on phase of the instant wave. This plus or minus which will depends on phase of the instant wave. Now simplify this expression, we get 2 mu t cos R is equal to 2n plus or minus 1 into lambda by 2. Here plus or minus which will depends upon the phase of the instant light wave. So this is the condition for bright fringe in thin films. Here, so whatever the wavelength lambda superimposing there, we get maximum intensity. That is, the thin film will appear bright. Next, condition for dark fringe. So condition for dark fringe, if the path difference is odd multiples of half wavelength, then we get dark fringe minimum intensity. These two are mandatory conditions for constructive and destructive interferences in thin films. So for dark fringe, path difference is equal to 2n plus or minus 1 into lambda by 2. Here the path difference already we found 2 mu t cos R plus or minus lambda by 2 is equal to 2n plus 1 into lambda by 2. Here plus or minus which will depends upon the phase of the instant wave. So we can simplify this expression, we get 2 mu t cos R is equal to n lambda. So path difference is integer multiple of wavelength and we get dark fringe. So whatever the wavelength superimposing, then we get minimum intensity, that is the fringe will appear dark. Next, in case of transmitted light, the conditions for bright and dark fringes are reversed than that of reflected light rays. Here for bright fringe, 2 mu t cos R is equal to n lambda. For dark fringe, 2 mu t cos R is equal to 2n plus or minus 1 into lambda by 2. So these are the conditions for bright and dark fringes in thin films in transmitted system. This is about interference in thin films. Here nowadays we are having number of applications of thin films. So they are applying on the surface of the solar panels to enhance the power of solar panels. This is about interference in thin films. Thank you.